which the theory of this problem we have discussed in the last class. What is the collision diameter? What is collision number? What is collision frequency? What is mean free path? All these idea we have seen in the last class. Today we are going to work out a problem using the basic idea we have learned in the last class. Look here, an astronomers have suggested that astronomers have suggested that intergalactic space contains hydrogen atoms. Watch closely. It is hydrogen atoms at a temperature of 7.8 into 10 power 5 Kelvin. Look at the temperature. It is so high, very high. With about 1 atom per 100 decimeter cube. See, very low pressure, very low pressure. Just only 1 atom of hydrogen is found in a space of 100 decimeter cube, but temperature is very high. Look at such a situation. This intergalactic space, temperature very high, but the gas molecules are found very far apart. If you take a volume of 100 decimeter cube, you are able to see only 1 atom of hydrogen. If it is so, we have already discussed the gaseous molecules are not stationary. They are all in a continuous random motion, and during motion they collide with each other, and the collision is perfectly elastic. They are not losing energy on colliding with each other. So in this given situation, you are asked to calculate the mean free path of hydrogen in the intergalactic space in light years. Light year means the distance traveled by light in 1 year. The distance traveled by the light in 1 year. Actually, the light is traveling a distance of 3 lakh kilometer per second. It is 2.8 into 10 power 8 meter per second. So what would be the distance traveled by the light in 1 year, which will be 2.8 into 10 power 8 into 365 into 24 into 60 into 60. So many meter. Please, gentlemen, mute yourself. So many meter a light will travel in 1 year. So we are going to calculate the mean free path of hydrogen in the intergalactic space in terms of light year. So light year, 1 light year is equal to 9.464 into 10 power 15 meter. So this is again a direct substitution. Lambda is equal to kT divided by root 2 pi sigma square p. Actually, this derivation itself we have seen in the last class. Why we have substituted kT and p here? We calculated the rho in terms of pressure and the temperature. So actually the rho, the number density, what we have seen in the last class, number density rho is equal to P by kT. So what I am doing, I am taking off this P and kT and I am substituting in its place the rho, which is the number density. So what is number density? Number of atoms found in unit volume of the space. What is given is the number density is 1 atom per 100 decimeter cube. So I multiply both numerator and the denominator by 10. What I'm getting is 10 divided by 1000 decimeter cube. 1000 decimeter cube is meter cube. So I can write there are 10 atoms per meter cube. There are only 10 hydrogen atoms per meter cube. So I substitute lambda is equal to 1 by the root 2 is 1.4146 multiplied by the pi 3.14 into sigma square. What is sigma? Sigma is the collision diameter of hydrogen, which is 200 picometer, which is 2 into 10 power minus 10 meter square into sigma square rho number average, which is 10 atoms per meter cube. And what you are going to get here is meter. So up to this point you are getting meter. The answer will be meter. See, meter square is there, meter power minus 3 is there. When they cancel out, you will get per meter. That per meter is in the denominator, therefore the unit is meter. So lambda is calculated in terms of meter, but what is asked is it has to be given in terms of light year. I have already said 1 light year is equal to 9.464 into 10 power 15 meter. Therefore the answer has to be divided by 9.464 into 10 power 15 meter. So what you are getting is 59 light year. So what is actually the mean free path? Mean free path is the distance traveled by an atom in between two successive collisions. Suppose an atom hits another atom now. What is the distance traveled by the same atom to get another hit? So in the intergalactic space, as the number density is very low, it has to travel a distance of 59 light years for the next collision to occur. So such a long distance it travels. So the reason is, one is the very low pressure, that is the number density is very low, and another thing is the temperature is very high. I have already told you when the temperature is high, the collision frequency will increase because of the increase in the kinetic energy. When the pressure is less, the collision frequency will be less because of the less number of molecules in space. And for the given condition, the mean free path of the hydrogen is 59 light years. And the next question is, you have to calculate the approximate average time in years between collisions of the atoms. So what is presented here is the distance. 59 light years of distance it has to travel for the next collision. Now, what is the number of years actually passed between two successive collisions? That is what we are going to calculate. Look here, the average time taken for the next collision, I can write it is the mean free path divided by average velocity. So mean free path divided by average velocity will give you the actual time passed between two successive collisions. Average velocity is square root of 8 RT pi into molar mass. It is 8 into R, 8.314 joule per Kelvin per mole, multiplied by 7.8 into 10 power 5 Kelvin. This is given. The temperature of intergalactic space is given. Divided by the pi value 3.14 into 1.0078 into 10 power minus 3. Actually, the whole thing has to be taken square root. The whole thing has to be taken square root. Power half you have to include. Actually, put a power half here. I think I can annotate. This whole thing has to be taken. Whole thing has to be taken power half. So what you are getting is 1.28 into 10 power 5 meter per second. So this is the average velocity. So what is the time taken between two successive collisions? Lambda we have calculated in terms of, see the answer we have got. It is meter per second. So we have to substitute the lambda in meter. So 59 into 9.464 into 10 power 15 meter divided by the average velocity 1.28 into 10 power 5 meter per second. So this meter and meter is cancelled. It is per second. It goes to the numerator. It becomes a second. So what you are getting is a 4.3623 into 10 power 12 second. So 1 year is equal to 3.156 into 10 power 7 second. Therefore, if you divide this answer 4.3623 into 10 power 12 divided by 3.156 into 10 power 7, it is taking 1.35 into 10 power 5 years. Okay, here, so many years it takes. 1.38 into 10 power 5 years it takes for another hit. But actually, if you look at the average velocity, look at the velocity. The average velocity is 1.28 into 10 power 5 meter per second. Look here. So if you multiply this by 60 into 60, you are getting 4.6 into 10 power 8 kilometer per second. Sorry, meter per hour. If you divide it by 1000, you will get 4.6 into 10 power 5 kilometer per hour. Look at the speed. Even jet aeroplanes cannot, even rockets or any other body cannot travel at this velocity. It's a very high velocity. It is of the order of 10 power 5 kilometer per hour. Normal hydrogen gas. It is traveling at that high speed. So I think I have discussed enough problems. யாரு அது